Good morning, everyone. I thank you all for joining in and giving us the opportunity to share our experiences with our engineering fraternity in the subject of rail structure interaction. We hope that this webinar will prove beneficial for all of us and we can take up these learnings and experiences towards further development. Today we are here to present our experiences with MIDAS rail structure interaction module, to present the simulations we have performed and our suggestions to MIDAS for further development of this module for benefit of both railways and bridge engineers. Let me first introduce myself. Myself, Akshay Vahal, and my colleague, Mr. Nitin Mittal, belong to the EDRC department of L&T Constructions, erstwhile L&T ECC. We will discuss about L&T Construction and EDRC department briefly in the following slides. Both of us will guide you through this webinar today, as we have been involved in extensive research on this subject and have successfully completed some projects on rail structure interaction. So we begin with a brief introduction of L&T Construction. Of course, most of you must be aware of who we are and what we do. Then we move on to discuss the basics of rail structure interaction, although the same has been covered in the previous webinar on 28th May, but we feel that it is important to make some statements towards the same for better linkaging of these concepts to the present webinar. Then my colleague Mr. Nitin Mittal will take over for describing the reference project of Delhi Airport Line and the live project that we have worked upon using MIDAS Civil. And finally, we shall state some requests on behalf of L&T and all the engineering fraternity to MIDAS for further development of certain features in this rail structure interaction module. So here we briefly introduce our company, L&T Constructions. As you all must be aware that L&T Construction belongs to the LASEN and TOUBRO group, which is more than 70-year-old company operating in various diversified business segments such as technology, engineering, construction, manufacturing. L&T Construction operates in 5 business verticals, namely heavy civil, building and factories, transportation infrastructure, electrical and automation, and power transmission and distribution. Mr. Nitin Mittal and I belong to the domain of transportation infrastructure. Transportation infrastructure deals with railways, roadways, runways, and our EDRC department belongs to the railways business. As you may see from the color coding, our penetration into the railways domain is much diversified, and we operate in most of the railway sector, right from electrification, railway systems to construction. The railways as SBG, or the strategic business group as we call it, to which we belong, operates in all the major sectors of railway segments, be it conventional mainline railways, urban metros and monorails, or dedicated freight corridor. Our EDRC department, which stands for Engineering Design and Research Center, works on all the design and engineering requirements of railway sector, such as bridges, buildings, tracks, temporary works, permanent works, alignment, etc. We are a team of 15 dedicated engineers and 4 dedicated draftsmen who work continuously towards our major design and engineering projects. Some of our major projects are, of course, Mumbai Monorail, first half or phase 1 of which has already been commissioned, and the second phase will be done by the year end. Second is Chennai Metro, which is also under execution. Hyderabad Metro, 160 kilometers, track construction is still under process. And finally, the dedicated freight corridor, which is the feather in our hat, and we take proud of having this project with us. And as you may be aware that all these 4 major projects which are in our portfolio are design and build. So you can see the importance of our department and why we are so focused on further development of MIDAS, because this is a very good tool for us. In the following slides, we will describe the basic theory and concepts, which you all must be aware, but just to recapitulate for the audience who are first time attending this webinar. As per the Indian Railways LWR manual, LWR are rail panels welded to more than 250 meter in broad gauge, and CWR rails are continuously welded throughout the project from the depot, including points and crossings. We consider CWR as a necessary evil, as it has its own advantages and disadvantages. The advantages are quite obvious, that CWR enhances the life of the rails and the wheels, as well as it improves the riding comfort, riding quality, and also considerably reduces the impact noise and vibration which are caused due to the fish plate joints. Of course, the key concerns for the railway engineers using a CWR is a possibility of buckling due to temperature increase and rail failure due to temperature fall. Both these significantly increase the risk of derailment, causing severe life threat, and therefore are one of the biggest concerns for railway engineers. Now, introducing a bridge under a CWR increases the complexity of design, as the bridge itself is prone to movements and deformations. The forces applied either on a CWR or on a bridge directly or indirectly affect each other. Therefore, there is a need for detailed understanding and detailed and accurate simulation in order to assess accurately this phenomena, which we call as rail structure interaction. In order to better understand this phenomena, we need to understand how a track behaves on a bridge. The fastening that we use on a track are elastic fastenings, which hold the rail down to the track using elastic tension clamps. These fastenings have certain resistance to movement of the rails, which is directly related to the load applied by these tension clamps. After the threshold resistance of these fastenings is reached, the rail slips and applies a constant load to the track structure. This can be seen on the figure on the right, the center one, where you can see there is a constant decrease in the toe load, or the longitudinal restraint as we call it, and then it starts to slip. The displacement becomes constant on, keeps on increasing on a constant load. In case of a ballasted track, there are two different types of longitudinal resistances. One is offered by the ballast to the sleeper, and the other is offered by the fastening to the rails. In case of a non-ballasted track or a slab track, there is no ballast, and all the longitudinal resistance is offered only by the fastening. This resistance is direct function, which transmits the load to the bridge underneath and also transmit the forces from the bridge to the track. This element of the fastening and the longitudinal restraint is key to accurately determining the effect of rail structure interaction and its effect on the bridge and the track. It also gives us somewhat of flexibility to change the forces, design the forces according to the structure that we have. If we reduce the toe load of the fastenings, we can also reduce the stresses that are occurring in the rails. And this is one of the very strong tools that is provided to the railway engineers to manipulate the stresses that are generated. From the bridge point of view, there are several considerations such as static arrangement or span arrangement of the bridge, the bearings, support, bending of deck, etc. With MIDAS, we have an advantage of either simply calculating the effective stiffness or the total stiffness of the structure, or simulating it in terms of bearings, just by applying a small spring at the end of the span, or modeling the complete support with all the data and letting MIDAS software itself accurately calculate the stiffness. We have used a combination of both of these approaches in our modeling, which will be explained in the coming slides by my colleague Nitin Mittal. In case of a fixed movable type bridge, we have used bearing definition, which amounts to the complete stiffness. And in case of a long span or a continuous span having an intermediate pier, that pier we have modeled accurately, and the stiffness is calculated internally by the software. As per the UIC standard for calculation of rail structure interaction, we have to consider three actions: thermal expansion of the deck, horizontal braking and acceleration forces, and bending of the deck. As seen from the first figure on the left, due to thermal expansion of the deck due to temperature rise, the free support, the right-hand side of the bridge, tends to move away, and it also pulls the rail along with it to the right side of the embankment. And therefore, on the right side, you can see that there are compressive stresses, and on the left side, there will be tensile stresses. The same phenomena happens also in case of braking and acceleration, the only difference being that the forces are being transmitted from the rail to the deck, which is opposite in case of thermal, where the forces are transmitted from the deck to the rail. On the right-hand side figure, it can be seen that when the bridge bends along its neutral axis, the upper end of the deck moves inwards due to reduction in length, and lower portion of the deck moves outward due to increase in the length. This again leads to longitudinal movement at the rail level, thereby causing additional stresses in the rails. As per the UIC, we have to check these effects of rail structure interaction in both SLS and ULS cases. In ULS, we check for maximum tensile strength and compressive strength, or stresses which are occurring, and compare it with the strength of the rails. These strength parameters are also defined by UIC. For example, in additional compressive strength that is allowable is 72 Newton per mm square, and the maximum permissible additional tensile stress is 92. Why we call it as maximum additional is because these stresses are generated solely because there is a bridge present underneath the track. In case of a standard track, whatever stresses are there, they are no longer a concern for us. Only the stresses, additional stresses which are generated because of the bridge, these values are the limiting factor for those. For SLS, principal checks are related to deformation, which leads to deconsolidation of ballast and thereby increasing need for maintenance. For our case, when we did the metro project, we did not have to check for SLS cases because this is not relevant for non-ballasted track, and metro projects are all non-ballasted. Now, the accuracy of rail structure interaction depends on the computation analysis that we use. Both UIC and MIDAS adopt a separate and staged analysis approach. This has already been discussed in the previous webinar by Bodhi Rudra. In separate analysis, the stresses due to the three actions discussed earlier are separately calculated and added to obtain the summation of stresses. In staged analysis, the thermal loads are applied and then the train loads are applied. The former analysis method is more likely to give more conservative values of stresses. This is explained in the next slide. As you may see from the figure on the left, in separate or simplified analysis, the loads applied cause deflection in the rails on the longitudinal direction. These deflections are independently calculated and the stresses are added. However, in practicality, thermal loads are always active on the track, even if the train is moving or not. This means that the rails are already breathing, irrespective of the train. Therefore, the threshold limit of the fastening system, which we discussed in the beginning, has already partially been realized by the thermal loads itself. Now, when the train moves and applies further loads over and above the thermal loads, the remaining threshold limit of the fastening system is also utilized, thereby causing a slip. This leads to the fact that the rails are now slipping over the fastenings and the constant load is being applied. There is no increment of load because of the increase in the loads due to train loads. Whereas in the second case, you can see that the forces due to temperature are applied first and then the train loads are added, and therefore this gives us the more accurate calculation of stresses compared to the simplified analysis. For computation analysis, we can list the basic input requirements for simulation. For the bridge, these are bearing details, dimension and properties of the pier and deck, elastic properties of the deck, height of the deck, neutral axis of the deck, lateral and bending stiffness of the foundation. Further to this, loaded and unloaded longitudinal resistance of the fastening, the rail sections, train loads, etc. We can provide all these inputs in the rail structure interaction module of MIDAS to very easily create the various models and simulation. This will be explained by examples of our two projects in the coming slides by my colleague. Now we move on to the two models that we have generated using MIDAS Civil. One of these models was for Delhi Airport Express, Metro Express project, which was one of my previous design projects, for which the simulations were conducted by our design consultant using their own proprietary software. We tried to carry out these simulations on our own and compare the results with the existing report to ascertain the correctness of modeling through MIDAS. I now hand over to my colleague, Mr. Nitin Mittal, to take over the description of what we did and how we did.
Thank you, Mr. Akshay. As already told, our first project of today's discussion is Airport Metro Express line. The RSI study concerns 19 span of AML in Dholkua area from P62 to P91, including Dholkua station and long span bridges SS1 to SS4. Client provided input data like rail and deck material properties, bridge configuration, rail and deck section properties, temperature and train loads, longitudinal restraints of fasteners, and stiffness of side piers and bearings. Based on these data, desired output were envelope for temperature variation of the deck, envelope for braking and acceleration loadings, combined envelope for temperature and train loads. Now I am going to explain how we generated model in rail track analysis wizard of MIDAS Civil with these input in next few slides. These were the input data for bridge configuration, rail and deck material and section properties. Here we can note that areas and modulus of elasticity were different for some span bridges, and COG to top distances are also different for some decks. So deck and rail material properties and deck configuration were given in layout tab of rail track analysis wizard. Here in the right screenshot, we can see how we assigned rail material properties as per given input. As areas were different, we assigned 3 general sections named 4.192, 1, 9.137 as shown in left screenshot. Assignment was done with help of input data like area and moment of inertia as right screenshot. Section property of rail UIC 60 is already assigned in program. We also assigned section named intermediate pair with ID 5, which will be discussed in later slides. Input of longitudinal restraints. As explained in RSI's introduction part, longitudinal restraints for track were provided as per UIC 774-3. For concrete bed, limit between elastic and plastic zone was 0.5 mm. Unloaded longitudinal maximum stiffness was 40 kN per meter. Loaded longitudinal stiffness was 60 kN per meter. These values were provided in boundary tab of the wizard as shown in right part. Here in this screenshot, this can also be noted that only one value can be assigned for horizontal point spring data. I shall explain in later slides how we define different values. Now coming to input of loads. Differential temperature in deck was 25 degrees Celsius. Vertical load was calculated on the basis of number of cars in train, length of car and value of force transmitted by one car, which is 27.2 kilonewton per meter. Kilonewton. Braking and acceleration load was taken 18% of vertical load as per UIC. As here are two tracks, so in this screenshot we can see in one track braking and in another acceleration load was considered as per UIC. Now this can also be noted. We provided 5 moves so that train can be accommodated on the entire considered length of the bridge. Program breaks the entire considered length of the bridge in a small element length. Here element length was given as 1 meter for higher accuracy and as per recommendation. So different move case files were created by program as per input values, including file for temperature as shown in right part. Input of span intermediate bearings. As there are some long span bridges in the scope of the problem, as explained earlier, which contains some intermediate bearings. For that, bearing stiffness was provided as input. From that, average heights and section properties were calculated as shown in this Excel sheet. As per UIC, for substructure system, either we can provide total horizontal stiffness directly or provide a detailed modeling of substructure. So what we did here, we provided detailed modeling in case of intermediate bearings. So column has been assigned as beam members. For that, firstly nodes were introduced by node table in each move case file, as shown in this screenshot. Supports conditions were assigned by support tables. Rigid link between deck and bearing provided by elastic link table. These are some screenshots of actual simulations. Section properties were assigned by element table for each move case file and temperature load file separately. Here in the lower rows of right screenshot, we can see section ID is 5 for intermediate pairs, which we assigned initially at the time of assignment of section properties. As shown earlier, there were different COG to top distances for some decks. Now what we noticed, that program took a random higher value for COG to top distances, and it applied to all spans. So what we did, we corrected COG to top distances for span by shifting the position of centroid of deck in nodes table. Here in this screenshot, we can see that rails are connected to deck by bilinear springs. As right span had larger value of COG to top distance, so we corrected accordingly. Input of side pier and bearing stiffness. Stiffness for side pier and bearings were given is as per data provided by civil bridge designers. Total side stiffness was calculated as shown in Excel sheet for temperature and train load separately. Here stiffness for train load and temperature load is calculated separately because shear modulus for short-term effect is considered as twice the shear modulus for long-term effect as per UIC 772-2. As explained earlier, with Wizard we can give only a single value for side stiffness. So again, we use point spring table for assignment of different values. Node number of supports were taken by model and total stiffness was provided accordingly. This is the screenshot for that simulation. So we can see how this table features in MIDAS gives us much more flexibility for providing inputs. Now modeling part is over. For different move cases, different models were generated by MIDAS according to train position. This is the screenshot for model view move case 4. I'll discuss why it is taken here. Coming to extraction of results, this was done by beam stress table as shown in left screenshot. What we did is we noted element number from model and extracted the results for axial stresses in rails for each move case file separately, so that output envelopes can be developed in Excel sheet. When the results were extracted, we found worst results were obtained in case of move 4. These are some axial stress diagram given by MIDAS for different actions. Stress diagram for temperature load, stress diagram for braking and acceleration force, and the third one is a stress diagram for vertical load. Development of outputs. We developed output envelopes in in-house Excel sheets. As per UIC, most unfavorable situations should be considered taking into account positive or negative temperature variations and different positions of the trains traveling along the bridges. These envelopes are based on same logic. Here this envelope shows stresses in rail due to temperature load only. Stresses in rail due to positive change of temperature in deck have been extracted from MIDAS file. For obtaining the stresses due to negative temperature change, results for positive change were multiplied by negative sign. This red curve shows compressive stress on each element of rail irrespective of negative or positive change of temperature, and the blue one shows tensile stresses. This is the envelope for stress in rail due to acceleration and vertical load. See, although we got worst case results in case of move 4, but here red curve shows maximum compressive stress for a particular element irrespective of train position, and the blue one shows tensile stresses. This is the combined envelope for temperature and train loads, which has been developed by summation of previous two envelopes. Now finally we got maximum compressive stress 98.5 Newton per mm square and maximum tensile stresses 99.3 Newton per mm square. See, these are the burst stress results for which we have done all the RSI analysis for this particular project. Moving to project 2. Hyderabad Metro is one of the projects that we are currently doing, and it is a complete design and build project as told by Mr. Akshay Bahl. Our EDRC team has been appointed as the official proof checker for all the track related design led by Mr. Akshay Bahl. The design consultant had carried out the rail structure interaction using their proprietary software, and we had carried out the simulation using MIDAS Civil to confirm and proof check these results. The RSI study for this project concerns corridor 3 between piers C3NGHP16 and C3HT5 TP5, including Hapsigoda station. Provided input and output were the same as the first project, like rail and deck material properties, bridge configuration, temperature and train loads, stiffness of side pier and bearings, and the output envelopes are the same. Material properties and section properties were given for the rail and deck section as shown in this diagram. Again, deck and rail material properties and deck configuration were given layout tab of rail track analysis wizard. These are the screens of sort for that particular project. General sections were provided in section tab of rail track analysis wizard for assigning section properties of deck. As areas were different for some spans, again different section properties were assigned for them, like 3.992, 4.094, 4.279. And section property of rail is already assigned in program as told earlier. Values of longitudinal restraints were given from UIC 7743, similarly as first project in bound detail. Input of different loads. Differential deck temperature was 25 degrees Celsius. Vertical load was 32.23 kN per meter. Braking and acceleration load was again taken as 18% of vertical load as per recommendation. As the train length was 126.6, so we gave 12 moves in move load data in order to get highly accurately results and highly accurate stresses. Again, element length was given 1 meter as recommended. Different files for different move cases were created by software itself, including temperature one. In this right screenshot, we can see we got 12 move case files, one simple train file, and one simple temperature, which is for temperature loads. There were some span intermediate bearings in an entire considered patch. So those were again introduced in model by using nodes, elements, elastic link, and support stable. Manual corrections of COG to top distances. This were again done as per the first project because program took a random higher value for COG to top distances. This was the input of side pier and bearing stiffness for this project. Total stiffness was provided by point spring support table and by taking nodes number of support table from model. Again, element number of rail elements were noted from model and results of axial stresses were extracted for all the 12 move cases. Move 5 was the burst move case, and these are the axial stress diagram for the same. Again, for axial stress in rail due to temperature load, first one. Second one is for axial stresses in rail due to braking and acceleration force. And the third one is for axial stresses in rail due to vertical load. Output envelopes were developed for temperature and train loads as explained earlier in in-house Excel sheet. First one is for stresses in rail due to temperature load only. And second one is for stresses in rail due to train loads only. This is the combined envelope for rail temperature and train loads. Maximum compressive stress was 72.4 Newton per mm square, and maximum tensile stress was 66.3 Newton per mm square. Here we can see the tensile stresses satisfy the UIC recommendation, which was stated in earlier slides by Mr. Akshay Bahel. Recommendation for rail track interaction wizard. These are the some points based on our experiences while we went through the RSI analysis for different projects. So I shall state some requests on behalf of L&D for further development of RSI wizard in next slide. First point, which we also discussed during modeling of projects, is manual correction of COG to top distances, which is highly time consuming. We want MIDAS to correct this modeling error. By current wizard, we can generate models train moving in opposite directions. In order to get worst possible case, we want both train to move in same direction. Third one, as we saw that for developing output envelopes, the stress results has to be extracted from each move case file. We want MIDAS to develop the envelope itself and preferably in Excel format directly. We would also like to MIDAS work upon development of turnout and crossover modeling in MIDAS, as the same become crucial in case these lie in the critical section locations. This is the information regarding upcoming webinar on June 10th. Again, Bodhi Rudra will be telling us about rail track analysis wizard, analysis, separate analysis and complete analysis. And the most important thing, he will be discussing about post-processing results, how we can extract the results from the given files which we developed during the modelings. Thank you everyone for joining us.